Just think about your day for a second. Your phone, right there in your pocket, the website you're probably looking at right now, your computer, all those smart gadgets in your house. We're constantly interacting with this digital stuff every single day. But have you ever really stopped and thought, what's actually underneath all that? What's the core engine making it all work? Well, today, we're doing a deep dive into someone pretty extraordinary, though maybe not a household name. We're looking at the contributions of Dennis Ritchie.
That's exactly right. And our mission here is to kind of unpack how this one person's work, often done, pretty quietly under the radar, actually became the fundamental DNA, so to speak, for almost every piece of tech you touch. You'll see why his legacy is just so incredibly important for, well, everything digital we rely on now, even if the name itself isn't instantly recognizable to everyone.
Yeah, it's fascinating stuff. And we've gathered some really good material for this. Excerpts from the Computer History Museum, Wikipedia, of course, and also a great profile focused just on Ritchie's life and work. Okay, so let's unpack this. Let's start right at the beginning. Dennis Ritchie, born in Bronxville, New York, 1941. He heads off to Harvard, graduates 63. Degrees in physics and applied mathematics. Pretty serious credentials.
Right, and what's really interesting, he actually went on to do a PhD also at Harvard in math. He even finished a draft thesis back in 68-something on computational complexity and program structure.
Yeah.
But here's the wild part. He never officially got the degree. The thesis itself was basically considered lost for, decades.
Lost? Seriously?
Yeah, apparently rediscovered only in 2020. It kind of paints a picture, doesn't it? Someone more focused on the work, the problem solving, than maybe the official piece of paper.
Wow. Lost until 2020. That's incredible. It definitely suggests his focus was elsewhere, beyond just, ticking the academic boxes. So after Harvard, where did he land? Where did the real foundational work start?
That's when he landed at Bell Labs, joined their Computing Sciences Research Center in 1967. And that became his base, really, for almost his entire career. He stayed right through its evolution into Lucent Technologies, retiring in 2007 as head of the Systems Software Research Department. Bell Labs. That was the place, the innovation hub.
Bell Labs, right. And that's where he famously teamed up with Ken Thompson, working initially on this thing called Multics. What exactly was Multics, and why was it, important for what happened next?
Multics was ambitious, think big. It was this early, very complex operating system designed for huge mainframe computers, aiming for a time-sharing multi-user environment, a really grand vision for its time. But complex is the key word. It got really big, maybe unwieldy. And it was actually Ken Thompson's frustration with Multics that kind of lit the fuse.
Frustration? How so?
Well, instead of just trying to fix Multics, Thompson apparently found an old, unused PDP-7 mini-computer lying around, a much smaller machine, and he basically started tinkering, writing his own simpler operating system from scratch. Ritchie saw what he was doing, got involved, and boom, history.
Just started over on an old machine. Love it.
Yeah. And the name UNIX, that actually came a bit later, around 1970. Brian Kernighan, another Bell Labs legend we'll mention again, suggested it. Kind of a pun, right? UNIX versus the complexity of Multics.
A pun that stuck. So, they ditch Multics, start fresh with UNIX. What made it so revolutionary compared to what came before?
Well, think about computers back then. Mostly one person, doing one thing at a time, and organizing files. A mess. UNIX introduced this elegant hierarchical file system. Suddenly, you could organize things logically, like folders within folders. Game-changing for managing data.
Okay, organization. What else?
And crucially, multitasking and multi-user capabilities. One computer potentially serving many people doing different things simultaneously. That made computing way more efficient, way more economical. It opened the door.
And this ties directly into Ritchie's other huge contribution, right? The C language. Because UNIX wasn't originally written in C, was it?
No, exactly. That's where things get really clever. Initially, UNIX was written in assembly language. Super fast, sure, but incredibly tedious to write, and, critically, tied directly to this specific hardware, like that PDP-7, not portable at all.
Right, so if you wanted to run it on a different computer, you'd basically have to rewrite huge chunks of it.
Pretty much. Or all of it. That was the standard problem. High-level languages existed, but they were often seen as too slow or not powerful enough for systems programming for writing an OS. Assembly was seen as the only way, despite the portability nightmare.
So C was the answer to that problem.
Precisely. Ritchie developed C as this brilliant middle ground. It was efficient enough, close enough to the hardware to actually write an operating system in it. But it was also a high-level language, much easier to write, read, and crucially, portable. They rewrote UNIX in C. Suddenly, this powerful operating system wasn't tied to one machine anymore. You could, with some effort, compile it and run it on different types of computers. That was revolutionary. Absolutely blew the doors open for software development.
And that portability, that core design, its influence is just staggering today.
Oh, completely. UNIX basically became the blueprint. You look at Linux, which is everywhere, right? BSD systems, Apple's Mac OS and iOS. Their foundations trace directly back to UNIX. Even Android uses the Linux kernel, which itself is UNIX-like.
It's like the grandparent of almost everything running our digital lives.
It really is, and Ritchie himself saw it that way. There's a quote from a 99 interview where he talks about Linux and BSD, saying they were essentially the continuation of ideas that were started by Ken and me and many others many years ago, acknowledging that lineage.
Okay, so UNIX is massive, foundational, but so much of its success and spread is down to C. Let's focus on C itself for a bit. Developed early 70s, Bell Labs, successor to an earlier language called B. What made C itself so groundbreaking?
Well, like we touched on, it hit this sweet spot. Portability right once, run mostly anywhere. Efficiency fast enough for demanding tasks like OS development, but also flexibility and expressiveness. It gave programmers a lot of power. Ritchie had this famous quote, "C is quirky, flawed, and an enormous success." And that kind of nails it, you know? It wasn't perfect, it had its rough edges, but it worked so well for what it was designed for.
Quirky, flawed, and an enormous success. I like that. So how did it become, as you said, the lingua franca for systems programming? Where do we see its impact most directly today, maybe in ways people don't realize?
Oh, everywhere, really. I mean, the core of operating systems, Linux, parts of Mac OS, Windows internals, heavily C, embedded systems. Think the tiny computers in your car, your microwave, medical devices. C is dominant there because it's efficient and close to the hardware.
Right, the stuff running inside the system.
Yeah. Exactly. And even many of the tools used to build other software, compilers for languages like C++, Go, Rust, even Python interpreters often have core components written in C for performance. It's the builder's language in many ways.
And of course, the book, You Can't Talk C Without Mentioning K&R, the C Programming Language, by Kernighan and Ritchie. Still a classic.
Absolutely iconic. It taught generations of programmers. And the influence just branched out. C++ obviously builds directly on C, Objective-C, which Apple used for years, C# for Microsoft. Even Java borrowed syntax and concepts. The family tree is huge.
It's also interesting he didn't just stop there. He was involved in other projects later, things like the Plan 9 and Inferno operating systems, another language called Limbo.
Yeah, always pushing boundaries. And that little tidbit about cracking the M209 cipher machine back in the 70s.
Right. With the NSA discussion leading to it not being published, shows another side of his intellect, that cryptanalysis angle.
Definitely. A truly multifaceted mind.
So given all this UNIX, C, the foundations of modern computing,
Yeah.
it's no surprise he received some major awards, often alongside Ken Thompson.
Yeah. The recognition eventually came, even though he wasn't one for the spotlight. The big one is the ACM Turing Award in 1983. That's like the Nobel Prize for computing. They got that for UNIX.
Okay, Turing Award 83. What else?
Let's see. The I.E. Hamming Medal in 1990, again for UNIX and C. He was made a Computer History Museum Fellow in 97. Then a really big one, the U.S. National Medal of Technology in 1999.
Awarded by President Clinton, right?
That's the one. The citation mentioned their work leading to enormous advances and stimulating growth of an entire industry. Pretty accurate, I'd say.
Understatement, maybe?
Maybe. Then there was an Industrial Research Institute Achievement Award in 2005 and the Japan Prize in 2011. Very prestigious, shortly before he passed away.
It's quite a list.
Yeah.
Yet everyone seems to agree he was incredibly modest, stayed under the radar.
He really did. He seemed genuinely focused on the technical challenges, the elegance of the solutions, not the fame. But that quietness means his impact isn't always fully appreciated by the public.
Which is where that quote from the computer historian Paul Ceruzzi comes in.
Yeah, the microscope one. If you had a microscope and could look in a computer, you'd see his work everywhere inside. It's such a perfect description. He built the invisible, essential infrastructure.
It makes that comparison people drew in 2011, when both Ritchie and Steve Jobs died within a short time of each other, really striking.
It does. Jobs was the visionary showman, the face of iconic products. Ritchie was the quiet architect who built the foundations that made so much of that possible, including, ironically, much of the tech Apple built its fortune on.
A different kind of impact, but arguably just as profound, if not more so in some ways.
Brian Krennan put it simply. Ritchie never expected C to get that big, but he said, the tools that Dennis built and their direct descendants run pretty much everything today. Everything. It's hard to overstate.
And the legacy continues, even in tributes like naming Linux distributions after him, Fedora 16, FreeBSD 9.0, and an asteroid 294727, Dennis Ritchie.
An asteroid. Seems fitting for someone whose work reached so far.
So wrapping this up, what's the big takeaway? What does this all mean for you listening right now?
Well, it means that the smartphone in your hand, the servers delivering this audio, the computer you might be using, they all have Dennis Ritchie's fingerprints deep inside. UNIX and C. They're not just old technologies. They are the living bedrock of our digital world.
And maybe a final thought from Ritchie himself, which captures the elegance he aimed for. UNIX is basically a simple operating system, but you have to be a genius to understand the simplicity.
Love that. Simplicity is hard. So here's something to think about. How often are the most world-changing innovations not the flashy ones we see advertised, but the fundamental, maybe even invisible building blocks created by quiet geniuses like Dennis Ritchie? What other unseen giants are out there shaping our world right now without us even knowing their names? Something to ponder.